Alright, suppose we have an electron in a hydrogen atom that at t equals 0 it has this wave function. Alright, so the way these are written are the first number here is the principal quantum number n, the second number is the angular momentum quantum number L, and the third is the projection of the angular momentum onto the z-axis, angular quantum number m. Alright, so first thing we need to do is find this normalization constant. So we're just going to normalize this wave function, alright, which we'll just call, let's just call it C naught. Alright, so what this means is that if we take the inner product of this wave function with itself, we should get 1. So, so let's go ahead and do that. So first we need the adjoint, or we need to turn these kets into bras. So for this side, right, so I'll bring the constant out front. We get the complex conjugate of whatever this A normalization constant is. And then we will have 1, 0, 0 as a bra this time. And now we need, whenever we see an I, we replace it by a minus I, right? So we have a minus 2I, 2, 1, 0. I just wrote that as a ket. I don't know whether I can make it look right. Okay. This is a bra. Plus 2, 3, 2, 2. I wrote this as a ket 2. Oh my goodness. Terrible. Have to think. Alright, now I can just copy this down as it is, because now I'm just writing this ket. So we have the A 1, 0, 0 plus 2I 2, 1, 0 plus 2, 3, 2, 2. Okay. Alright, and all of this is going to be equal to 1. So let's go ahead and get this done. So 1 is equal to, bring the constants, these normalization constant out front, A star A. And then anytime we have, so these states are orthogonal, so that whenever we have like a 2, 1, 0 multiplied by a 1, 0, 0, that is going to go to 0. So the only ones that are going to matter is when this is multiplied by this is multiplied by this, and this is multiplied by this. And these states are also normalized, so, well, let's write the first one out. 1, 0, 0. Inner product with itself, this is going to be equal to 1 because it's normalized. Okay, so this will go to 1. All right, and now we have a minus 2I multiplied by a positive 2I. All right, and then we would have this 210, 210 inner product with itself, which will also go to 1 because it's normalized. Okay, and then we'll have this 2 multiplied by this 2, so 4, and then of course 3, 2, 2 inner product with itself, which is also 1. So what we get, we have this A absolute value squared. Here we have a 1. So these i's are going to give a minus sign. 2's will give a 4. The minus signs will cancel. We get a plus 4. We have a plus 4 here. Okay. So, and this is equal to 1. So adding this up, we get a 9. So 1/9 is equal to absolute value of A squared. Therefore, A is equal to 1/3. Keeping it real. Okay. So, great. we've just normalized our wave function. So now anytime we see an A, like up here, we'll just plug in 1/3. So now we'll find the expectation value of the energy of this electron at t equals 0. So this state up here. And we'll express our answer in units of electron volts. All right, so finding the expectation value of the energy. Okay, the principal quantum number will tell us that. All right, and so what we do, we call this C naught, right? Put our Hamiltonian in there, sandwich it between these guys, and away we go. So now we get to have all of this written out again, I suppose. Yeah. Let's just look at the square of these different coefficients. All right. So acting here on the A1, we'll get an acting here on this first one, we get the n is equal to 1, so we get, I'll just call it E sub 1. I'll call this one E sub 2 and E sub 3. Should we go through the, yeah, let's just go through the whole thing. All right, we've written it like this already, so. All right, here we go, here we go. Constants out front, we'll have two A's, that'll be 1/9. So A squared is 1/3 squared is 1/9. And I'm just going to bring the terms out that we will be needing. So all the other terms will go to 0, because when we act with this Hamiltonian on this state, we just get a constant which will come out, and then we'll be left with just the inner product of these states. So this one, this Hamiltonian acting on this state will give us an E1. All right. Before we had this coefficient 4, which came from this 2i multiplied by its conjugate minus 2i. All right, and then acting on this state, we get an E sub 2. And then what's left over is 210, 210, inner product of itself, which goes to 1. All right, and then finally we get a 4 acting on this state. N is 3 for this one. E3, and then same story, 3, 2, 2. Just babbling on, babbling on. Okay, this also goes to 1. All right, so here we go. Our expectation value for the energy, I wrote this equal sign twice. 1/9 E1 plus 4E2 plus 4E3. So if we take a gajillion measurements of identically prepared systems, this is the value that we would expect to get for the average of all of those. So one thing we need to do is, let's put E2 and E3 in terms of E1. So we know for the hydrogen atom, E sub n is equal to E1 divided by n squared. All right. So this expectation value equal 1/9, we get E1. So here n is 2, so n squared is 4. So dividing by 4 just gives us another E1. Alright, so all we did was plug this E1 divided by 4 in for E2. E1 divided by 4 multiplied by 4 is just E1. Alright, so now we get, now 3 squared is 9. So here we have, and it doesn't cancel out, we get a 4/9 E1 out of this guy. So our final answer here for the expectation value of the energy, what do we have? G. So this would be 9/9, 9/9, and 4/9. So we have 18, we have 22/9 multiplied by 1/9, we get 22 over 81 E1. Okay, and E1 is equal to minus 13.6 electron volts. And so now we've expressed our answer in electron volts. Let me plug this into my phone really quick, just to give us a decimal answer. So 22 divided by 81 multiplied by 13.6. That gives us, this is a minus from this minus sign, minus 3.69 electron volts. Alright, so that's the expectation value of the energy for this state up here. Now, if a measurement of the z projection of the electron's orbital angular momentum is made at t equals 0, so still this state right here, then with what probability are the results 0, h bar, 2 h bar, and 3 h bar obtained? So we'll be looking at the third number in this set, the m quantum number, right? So if we run an LZ on our original ket here, our state, what have we got? Well, we would do a similar thing, right? Well, we would, I guess what we're doing is we would have, we'd make this sandwich of our operator to get our expectation values and different things. But the bottom line is that we would just find the mod squared of each of our coefficients in order to find the relative probabilities. So they're all multiplied by 1/3 out here. So let's just write this. Yeah. Let's just do this. So we get a squared, so 1/9 of the eigenvalue of this one for m is 0. Do we want to do this this way? I don't know. I'm just writing this here to remind us that this is that what we would measure if we got this. Well, I mean, okay, let's write the 0 h bar out, because if we're going to set this equal to this, I guess we need our eigenvalue there. All right. Then we had 4. So again, the absolute value squared of 2i is 4. And then we have to have our a squared as well. So we have a 1/9 with a 4 on top, so 4/9. All right. by the way, this thing's going to go to 1. I'm not going to even write it the second time because we'll just keep track with our h bar. So when we act with the LZ on this state right here, we pick out a 0 h bar for our angular momentum along the z-axis. And then this final one, again, 2 squared will give us 4 again, divided by 1 over 3 squared when we square the a as well, another 4/9. And finally we get something other than 0. So here for our m, we have a 2. So we get a 2 h bar. All right, so our 3 measurements are the different values we can obtain. Well, let's specifically look at the ones it asks for. So 0, I'll put an h bar here, 1 h bar, and then it's just 2 and 3. All right. We don't have any 1s or 3s. We only have 0 h bars here and a 2 h bar here. So the probability of 1 is equal to 0 and 3 is equal to 0. 1/9 plus 4/9 is 5/9 for our 0 h bar. So the probability of measuring 0 h bar along the for the projection of our angular momentum along the z-axis is 5/9, and the probability of measuring 2 h bar is 4/9. I'm sure there was a much better way of explaining this besides doing this whole expectation operator thing. Anyway, it was just looking at our values for m wherever they went. They're on this page. Looking at our values for m, and then we just take the absolute value squared of the different coefficients here, of course with this a distributed in there as well to keep it normal. And it did keep it normal because we see that our probabilities add up to 1. 4/9 plus 5/9 plus 4/9 is equal to 1. All right. Gee. All right, so finally, we're just going to write the time-dependent wave function. So here it is at t equals 0. Let's see how this guy evolves in time. So we want to know for some time later, what's it going to look like? Okay, any time after t equals 0. So we still have our a. Let's just write them in now this time. So we have 1/3, and then we have our these are 3 stationary states, right? But they are going to have phase that depends on time. So we just tack on our e to the minus I e t over h bar. But we have to remember these have different energies as well. So we can't just like factor this guy out to the end. This one has an energy of E1, right? Let me come down to the next line here. 2i, so 2, 1, 0, and then we tack on our other, our little phase for the time dependence. This has principal quantum number 2, so it's minus I e sub 2 t over h bar. Okay, and finally we have our last one, which has principal quantum number 3, e to the minus I e 3 t over h bar. All right, so, and then just as a reminder, rather than plug this all in and do all the simplification, let's just write our 3 different e's out here. E1 is equal to minus 13.6 electron volts. E2 is equal to E1 over 2 squared, which is 4. I'll come back. I'll do this with these equal in a moment, I guess. If we want the decimals, E3 is equal to E1 over 3 squared, so 9 on the bottom. All right, let's see what we've got here. Pull out the old calculator. So 13.6 divided by 4. Well, that was easy. 3.4 electron volts, and 13.6 divided by 9. We get a 1.51, and this repeats, by the way, if anyone cares. So about 1.5 electron volts. Okay, great. So putting these energies in, I mean, you could even, you might be able to pull out some factor if you split them all up based on E1 or something, whatever, who cares. Plug these values in these 3 places, and that will tell you how this state will evolve in time.